Hi there. I thought we'd look at one more example of working with set equality. Again, one of the most challenging parts of doing these is that one leap of faith where you're trying to go from an intersection to a union. Usually I like to have one sentence where I just explain, where I wrap the words in such a way that it allows me to get to the next step. And we'll go ahead and illustrate that here with this distributive law. Okay, so we want to show that if we intersect A with a union of B and C, that's the same thing as intersecting A and B, intersecting A and C and finding their union. We've already seen this in an intuitive sense where we've drawn it out in Venn diagrams. But now we want to provide some fail-safe proof because, again, think about all those different ways in which we can draw three sets. To show that the shadings are equal is fine, but we would need to do that for every possible orientation and situation in which A, B, and C are in. And there are a lot of them. Trust me, there's a lot of them. So we're going to first of all start off with the first statement that we need to prove, which is that the intersection between A and B union C, that an element that is in here also lives inside of the intersection between A and B, or the intersection between A and C. Okay, so we already know that in order to construct this Venn diagram, we would have to find the union of B and C and then shade that with what that set has in common with A. But when we're going to do this with what we call the element chasing method, which we're going to start an element inside of the first set and show that it's also in the other one. So by definition, we're going to say that let X be an element of A intersected with the union between B and C. And we're going to slowly deconstruct this in as many steps as we need to in order to make the logical connective between what we have over here. So this means, just by definition, I'm first going to define the intersection, that X is an element of A and X is an element of B union C. Alright, so we know that X is definitely an A, and we know that X is definitely an element of B union C. What we need to show is that X has to be in A, and it has to be in B, or it has to be in C. So let me take this one step further and say X is an element of A, and X is an element of B, or X is an element of C. All right, well, this is an AND statement, right? X is an element of A, and X has to be an element of B or C. So by virtue of this, this is where I'm going to make that leap of faith. This means that X is definitely in A, is definitely in A, but it also has to be in one of B or in C. Okay, so that means it definitely has to be in A, but then it also has to be in B or it has to be in C. So if I kind of think about this way, X is definitely in A, and it's either inside of here or it's inside of here. Well, by that very nature of what I just said, that means that X is an element of A and B, because it definitely has to be in A, but it has to be in one of these two as well. So X is an element of A and X is an element of B would work, or X is an element of A and X is an element of C would also work, because in this case, we guarantee that X is an A and it's in one of the other two. This is where our logical leap took place, where we had to kind of deconstruct the meaning of these words. X is in A and X is in B means that X is in the intersection of A and B by definition of what it means to be in both sets, or X is an element of the intersection between A and C by definition of what it means to be in both in A and in C. All right, well, that means that if X is an element of A intersect B, or it's an element of A intersect C, by definition of union, this means that X is an element of A intersect B, union A intersect C. And so we've just shown that an element that lives inside of this thing on the left is now also shown to be an element of this thing on the right. Now we have to work backwards. This is a step that kind of seems redundant, but it's not, because sometimes these things are a little bit harder to do when you're working backwards. But let's try it. X is an element of A intersect B union A intersect C. Oop, I don't want to show that yet. I just want to say we're going to show that these two things are subsets. That basically the thing on the right-hand side is a subset of the thing on the left-hand side, A intersect B union C. So I'm going to do the same thing. Let X be an element of A intersected with B union A intersected with C. And I'm going to deconstruct and I'm going to work backwards. Really the only difference is where we have to use that one logical statement to kind of turn ands into ors. Here we go. Okay, so X is an element of A intersect B. That's given. Union means it's in one or the other. So it's X is an element of the first thing or it's an element of the second thing. And furthermore, I could break that down to say X is an element of A and X is an element of B, or X is an element of A and of C. Well, in either case, I see that X definitely has to be an A. Right? I see that X is an A, and it's in one of two sets. It's first of all, it's an A and it's in B, or it's an A and it's in C. Therefore, by virtue of that, and I'm going to write this out, in both cases, or in either case, X is in A. It also has to be in one of B or C. So all I'm doing is using my words to deconstruct what that whole statement actually means. X is guaranteed to be in A, but it also has to be in B or C. Well, by virtue of that sentence alone, that allows me to say that X is definitely an element of A, and it has to be in A or in B. All right, so I can put parentheses around that if I want to say that it's definitely an A and it has to be in one of those two things. And now I can further break that down to say, okay, well, X is an element of A. X is in A or X is in B by definition means that X is an element of the union. Now, by definition of intersection, for an element to be in one set and to be in another set, it means that X is an element of A intersected with A. Oh, wow, I used A here. I'm sorry about that. This should be B. Let's try that again. One of these has to be B, one of these has to be C. So X is an element of B, or X is an element of C. Therefore, X is an element of B union C, and because X is in both of these two sets, A and in B union C, that means it's in the intersection between A and B union C. And I've arrived at my conclusion, which is that if X is an element of A and B, or it's an element of A and C, then it's an element of A and B union C. Now we got to be really careful. The definition of intersection means and. It's in one and the other. The definition of union means it's in one or the other. So while it may seem like we're just doing a bunch of these subtle movements, what we're really doing is deconstructing symbols into words, and then reconstructing words back into symbols to rearrange things in the shape of all of those sets to achieve the desired outcome. Now, this is not going to be possible when two sets aren't equal. You don't have to worry about that. As long as our language agrees with the symbols and we're using the strict definitions of union, intersection, set difference, we should not encounter any problems at all. If two sets aren't equal, then you're going to run into a hiccup somewhere along the lines. I hope this extra example has been helpful.